Daily Leet Code, day 56 of Daily LeetCode. We are back once again. We are still locked in the prison that is called longest nice substring. However, we've reached our maximum allotted time for this problem. That being said, it goes on. That being said, we got to move on, right? Because there are future problems to do, future problems to conquer. But I think what was our max time complexity that we reached, I think, was n squared. Yeah, I think that was no. I think our best solution was n cubed, and then yeah, I think it was n cubed, and then we had another solution with some optimizations, but that didn't really work that well either. So at this point, I'm thinking the best that we can do is read the solution, right? Because I think we spent at least 3 hours on this problem so far, right? And I think we're just out of possible methods that make sense. The three methods that, yeah, right. So we're looking, yeah, so we're just going to read the solution, right? And then we have no cards due today. So that being said, in terms of the weighted problems that remain, we'll probably do 30 minutes of weighted problems, and then we'll go on to do, I think, what we were stuck on before, which was a DFS Explore card, right? We were stuck on the DFS Explore card. Oh, no. I think it was, yeah, I think it was the DFS Explore card, but honestly, if you could go back to the Union Find Explore card, which was still the DFS Explorer card, just go back to the top. That way we know we're making consistent progress through the topics. There's also a couple of topics like Divide and Conquer that we probably want to brush up on, that we just don't have a good grasp on. That being said, I think being blocked by problems is actually turning out to be a good thing in a strange way. So I'm going to read, we also got our boy Thomas, who commented, right, gave us the secret solution. I think we also said we'd go through, right, because we have to make sure we ingest the solution, right? I think there was a discuss page here. Okay, my Chrome tab is frozen, but I think there was a discuss page. So if you wait for it to become responsive, okay, we'll just exit the page. So we're going to discuss. There was another solution that I wanted to read, and I think, oh no, it was crazy. It was like crazy long. Yeah, it was sliding window Java 26 by N, and this is something this is just crazy. But I think we have our boy Thomas, I think, has a similar solution. So let's see if we can make this make sense. So here's my solution. Any solution at worst contains 52 unique characters, right? True, right? Because if it's nice, right, then if it's 52 unique characters, right, the character is any solution at worst contains 52 unique characters. Well, the problem was if the string is nice, right? The worst case, right? Yeah, the worst case solution, we have 52 unique characters, right? Because for any arbitrarily long string, we could have lowercase and uppercase characters. So it'd be 26 times 2, right? That's if lowercase a, capital A, lowercase b, right? See all appears. And for nice substrings, unique characters would compare in 2s, e.g. A, as you can't have A, B. Not nice. Unique car equals 3. So brute force 52 unique characters. For each iteration, add to window or shrink/add into window based on the current number of unique characters. And guaranteed to find a solution since you have checked all the windows with total unique characters equals 2. linear characters equal 4 to 50, so it's O of 26 to n. Any solution at worst contains 52 unique characters, right? That's if A, B. Oh, I forgot to load up our timer. And at the same time, I forgot to finish the reflection. I just started jumping into understanding this problem. But yeah, you want to make sure to join the HCC, the Hyperbolic Coding Chamber. There are thousands of people joining every single day, right? One of them is Thomas Wang. I think he also just finished up talks with Elon, so I think Elon's actually going to hand over CEO to Thomas soon. So yeah, you're going to want to tune in, right? Because we're going to have the CEO of SpaceX within Discord, and it's a very good network to have. That being said, we have 1 hour and 30 minutes that remain today of prep, and then we have some channel comments and so we're trying to understand Thomas's solution to sliding window nicest substring. So brute force, so let's start over. Any solution at worst contains 52 unique characters, right? That's if, right, so I understand that any solution at worst contains 52 unique characters. And for nice substrings, unique characters would compare in 2s, right? Nice substring, unique characters would compare in 2s. Unique character equals 3, or 3 minus 1. So brute force, 52 unique characters. For each iteration, add to window or shrink / add into window based on the current. For each iteration, add to window or shrink / add into window based on the current number of unique characters. You're guaranteed to find a solution since you have checked all the windows with total unique characters. Yeah, I think we're gonna need our boy to send us the code on this one in the HCC. So I'm gonna get the code from our boy in the HCC, and then yeah, we'll do a closer in-depth review tomorrow. But I think this one I think I'd have to see the code for. It sounds similar to this one in a way, but actually I want to see what other what we also have here. This also looks like a brute force version. Oh, actually this looks like a divide and conquer version, which we can still learn from, so we'll keep this in mind. Actually, we'll keep the Python solution in mind. Actually, they're both Python, so it kind of doesn't matter. I wonder if there are any more linear times. This one, wait, this is what we just clicked, I think. Scala recursive O of n. This one is this Python simple maths, which makes me think there's a bit manipulation approach here. JavaScript simple. So we have a couple here. We have divide and conquer, right? This one says simple maths. So it looks like we're doing n squared iterations here, right? And then we're actually doing a, what's the time complexity on this? This looks like, time complexity in this looks not well. We're doing a for loop over the characters, right? So it's going to have n squared, and then we're going to do it if self DFS. To do I in S, right, where is I even coming from? Oh, no, this is a character. So for each character in S, I'm going to check if is lower and upper 9S. I think this is a linear, not an n, is in a linear time check, right? It has to be, right? Because we don't have a set. So I think this is linear. There's no way that this is, right? Then we sort at the end. So even then we do n squared plus n log n. And then we'll be dominated by, I think we need the graph, but n log n and squared. I think it'd be dominated by n squared. Okay, so now this seems to, this does look like a linear time solution here. Sliding window, showing if s.length is less than 2, right? If it's less than 2, right, then it can't be nice, right? Because at minimum you need at least 2 characters to be nice. So they're using an object here to cache the results, it looks like, or basically I think they're just wanting a way to look up a value in constant time. And they're using an object here and just setting the properties equal to the character, right? And then to check, I can just say if object has the property, right? And then what they do is they iterate over the whole string and they have the character, right? And they say if the character has an uppercase and a lowercase, right, we continue, right? Okay, so this actually, okay, so let's take a screenshot of this code and let's actually take it over to so we're looking at this current longest nice substring version, but we want to take it back to the current problem description. So we can actually block our current solution, right? And we'll have the original string that we had, right? So we'll say for const I of s, right? So we have basically creating a set, but the object version of it in vanilla JavaScript. And you can do it with regular JavaScript as well. I will equal to 0, I is less than s.length, I plus plus, right? Then if element is equal to s sub I, right? And if, right, we have an uppercase and a lowercase for this particular letter, right, then we're going to continue, right? So we have an uppercase and lowercase for this particular letter, so we're going to go to the next, right? And then on the next iteration, we're going to have an uppercase and a lowercase for this particular letter. And then Z is when we're not going to have an uppercase and a lowercase for this particular letter, right? Then we're going to say our current index, right, is actually at 0, 1, 2, right? So prev is going to be equal to the longest, oh. This is a divide and conquer. No, it's a sliding window. I've never seen a sliding window recursively. So we're going to get the prev, which is going to be the longest. We're going to have uppercase and lowercase. right? So we're going to go from 0, right, our current index, right, up until this first pairless character, right, which is actually going to be y and a, right? And I think substring is actually exclusive, right, of the end. So we're going to have y and a, right? And then what we're going to do is we're going to create a map, or basically a substring. Basically going to create a cache, right? And then from there, we're going to iterate over the string ya. We're going to get the element. And we're going to say, okay, does, oh, I see. They pretty much mixed up the longest nice substring and the linear iteration into one bit. So we'll say the previous substring is going to be equal to 0, basically, right? And it's actually, right, it's going to be equal to 0, basically, right? So when we start at ya, I is going to be equal to 0. I is going to be less than s dot length, right? Do we have an upper and a lowercase for y? No, right? Then we go to a. Do we have an upper and lowercase for a? No. So we return an empty string for previous, right? And for next, what do we do for next? So we go from I plus 1, so a, right, going to y, we're going to call the longest nice substring of that, right? That's going to be, we're going to get all the characters into an object, right? We're going to get that character, and then we're going to say, is there an upper and lowercase for a? Yes, yes, yes. From 0 and going to I, let's say we're in here with y, right? So that's where we are, right? And then do we have upper and lowercase? Yes, yes, yes. And as soon as we get to y is when we actually don't have an both uppercase and lowercase, right? And then from here we do const prev is equal to 0 going to I, right? And 0 going to, right, they're going to subtract the last string we used. This is going to be nice, right? And if prev is greater than next, greater than or equal to, right, then we're going to return prev, others are going to return next. I don't necessarily think this is linear time, though, at least this version, right? Because we'll have linear iteration to the string to create this object, right? This set of sorts. We have to iterate through the string. So for ya, we just iterate through it and check if it's nice. And then we do the same thing for y. So I wish he'd mentioned the time complexity for this. It's interesting though, because I've never seen a sliding window with recursion, so it's definitely something we're going to want to keep. Common area concept. Yeah, I've never heard of that, so that's very, very interesting. And then here we have a divide and conquer solution, which is similar to what we just saw actually. And that's kind of what they had. They had divide and conquer solution. We have the same thing we have here. They create the set, except it's a one-liner in Python. Iterate through the range, right? If s sub I dot swap case not in store, right? They're checking at the opposite case here. Swap case has, Python has a function called swap case, which lets us check the opposite of the current case, right? And you want to take the max of left and right, with the key being the length of them. This is interesting. I'm not seeing the divide and conquer is not giving. I wish there was a discussion post here to figure out. This one said, is there any n or log n solution? I think the only one, scalar recursive n. What if it's just This original one down here looks like it actually is. Could be linear time, but it looks like it's more building a system. This one seems to be linear time, but I have no idea how Scala works. Brute force sliding window based on unique character pairs in current window from 1 to 26, therefore. Based on brute force sliding window based on unique character pairs in current window. Unique character pairs in current window from 1 to 26. This is an absolutely monumental function. And this guy said, isn't this an LC easy? Yes, no. If you want to do force by, if you want to brute force, I don't think it's an easy. Yeah, this looks like more of a system. We have a for loop through, we have a while loop, right? It seems to do some work to fix some things. We have an else, right? So this is a little too, I think there's a lot going on here, but I guess I'm struggling to see, Bit manipulation plus divide and conquer. Still using divide and conquer here. Yeah, I think what's best for this problem is, while it makes sense, I think best case is in the future we return to it with a brute force version. I mean, with a sliding a divide and conquer explorer card in the future. That being said, I think we have about 15 minutes, so I think we should maybe we should focus on review, but getting the best time we can get. Right. So I think we should be okay. So let's do some weighted problems here. We're saying does dot sort return a value? I'm also curious, what's the best binary tree vertical order traversal? I think what's the best time complexity for this, right? Best time complexity or goal, time goal, right? Space goal, right? We have binary tree vertical order traversal, right? Given the root of a binary tree, return the vertical order traversal of its nodes as values, right? From top to bottom, column by column. If two nodes are in the same row and column, the order should be from left to right, right? So we have this input of a binary tree, and the vertical order traversal of its nodes would be 9, 3 and 15, 20, and 7. And so from here we have an interesting case, right? We have 4, 9, 3, 0, and 1, 8, and 7. We have 4, 9, 5, 3, 0, 1, 8, 2, and 7. Right, the number of nodes in the tree is in the range 0 to 100, so we know that our tree can be empty, and therefore we should probably output an empty array. So just to start, we could do that. If not root, right, return an empty array because there is no vertical order traversal. Right, but there seems to be two things we're interested in, right? We want the vertical order traversal, right? And to do that, there's generally, right, going to be a way to view this, right? So we can visualize this as a matrix, right? Where 3 is actually going to be our top row, right? This is going to be our 1st row or 2nd row. This is going to be our 3rd row. And so this still, right? This seems to be okay, but additionally, right, we're also going to want our columns to, this is what we're interested in, right? Our columns, right? And our columns is what they actually want arrays of, 9, 3 and 15, 20, and 7. Now to do that, what we could also do is define 3 as our 0th column, right? And if we go left from a node, we can either decrement from our current column or increment from our current column. So if 3 is a column 0, right? Going to 9 will be a column of -1. Going to 20 will be going to column 1, right? And then going left from 20 will actually give you a current column, which is 1 minus 1, which would be column 0 for 15. And then going right from there would actually give us column 2, right? So we can use this column order, but additionally, we're going to want to layer a top-down order as well. And we can do that with a level order traversal combined with matrix visualization. Now, if we do that, oops, I clicked discuss, right? I think our time complexity here, right, would actually be linear time, or yeah, because if we start from 3, right, if we want the vertical order traversal, we're going to have to visit every node in the tree, right? To visit every node in the tree, I see it, right? So to visit every node in the tree, we're going to have to pretty much append it to a map of some sort, right, where we can know what column exists, basically. I mean, what column a node belongs to, right? So if we iterate through, right, we'll have access to the node, right, and what column it's in, right? Then from there, we'll have a map that looks something like this. -1, right, would map to an array of node values, which would be 9, right? Then we'd have 3 more, we'd have 0, 1, right, and 2, right? For 0, we'd have 3 and 15, right? For 1, we'd have 20, and for 2, we'd have 7, right? Now, that doesn't necessarily mean also the order that we would have this map in, right? So we could have it in a different order. So what we also end up doing is having to do an n log n sort, I believe. Let's think about that. If we do a level order traversal, visit 3, then 9 and 20, right? And then if it has any children, right, then 15 and 17. So it should be ordered relatively right in terms of the row if we do a level order traversal. So I think it's possible that we'll need to sort the keys, and if that's the case, then we'd have n, right, n log n, right, linear time to visit the tree as well as linear space, but then n log n to sort it in terms of time. Now maybe that's not okay. Right, and if that's the case, right, we'd have n, right, but n log n would dominate, so this would literally be an n log n operation with linear time and linear time for space, right? If we could remove the sort somehow, then we would be fine. I actually think we could remove the sort with a linear time iteration, actually. So I actually don't think you need the sort. All we'd really need to know is our smallest column, right, and our largest column, and we could just generate an array, right, by looping over this range, right? By looping over this range, right, we could just generate an array, right? So for example, if we know that our largest column is -1, and our smallest column is -1, our largest column is 2, right? What we'd like to do is -1 through 2, right? And we can iterate over that range. We can just say, well, certain value is less than our largest column, we're going to add 1. Then we'll grab those values from that array and insert them into our output. Right, this would give us actually linear space because we wouldn't have linear time since we wouldn't have to sort, and also linear space. So let's try this. All right, so we want to do a level order traversal combined with matrix visualization, right, to create a map that is a pair of keys, which would be the column to the values. All right, so to do that, we'll say const map is equal to new map of number, right, to an array of numbers. I think presumably that's what they'd like us to return in the end. And then we'll also, right, to do a level order traversal, we're going to need a queue, right? And usually just has a root node to start, right? But we're also going to do it like this, where we'll have a root node, right, and a column, right? And so what we're going to have is a tuple of tree node, right, and number, and it's going to be an array of these tuples. Then we can say, well, q.length does not equal 0, right? What we're going to want to do is get the node as well as the column by doing equal to q.shift, right? We'll have a node and a column. We'll do q.shift, right? So we'll have the node and the column, right? So now you want to visit the left and right children of this node, right? But only if the node exists, right? So if node exists, right, then we presumably, right, if 3 exists, we'd like to visit 9 and 20 as well and be able to add it to our map, right? So if that's the case, we'll take the map, right? This is going to be a map that we're going to, right, first want to get the array. So we're going to say if we're going to get const r is equal to map.has, right, an array for this particular column. Then we want to get that value, right? Another way to simplify this is just to do map.getCall. If it doesn't exist, we'll set it to an empty array, right? Then we're going to do r.push, right, node.val, and then we'll do map.set this particular column to this new array that we've added a value to. Now, additionally, what else are we going to need here? We also want to visit 9 and 20. How do we go about doing that in a way that makes sense? Right, so we want to add them to the queue, but only if they exist. So we'll say if node.left, and what we'll do is push a tuple onto the queue, and what this tuple is actually going to be is going to be node.left as well as column -1. Right, then we can duplicate this and do node.right, right, and do call +1. This way, 9 and 20 are pushed onto the queue with their respective columns, and then we'll be able to do the same work. So this makes sense to me to start. I kind of want to print this map just to make sure that it makes sense. We'll turn an empty array to start. So while the queue length is an empty, we're going to start with a root, right, and 0. 0 is our 0th column, right? The node is going to exist because we're going to pull this off the queue and destructure it into this these two constant tuples. If the node exists, right, we're going to get the column. We're going to get the array for this column. Otherwise, we're going to create it, push the node's value on, and then set it equal to that column. And then we should have a map that makes sense, right? We have 0. Oh wait, yeah. I ended up pushing node.left, right? We're going to want to push node.right. So now this makes more sense, right? We have 0, right, which is 315, -1, which is 9, right, and 1, which is 20, and column 2, which is 7. So this is exactly our output that we want, except, right, previously we would have to sort our keys, dominating our time complexity with n log n, right? And then what we can do instead of doing that is just keep track of our smallest and largest key. So let's say smallest key. We're going to do is say let our smallest key, right, equal infinity. We're going to let our largest key equal -infinity. And we'll just keep, not our largest key, our largest, smallest call and largest call. And then from here, right, we're just going to want to keep track of these values, right? So we're going to say smallest call, right, equals the math.min of smallest call in the current column, right? Same for largest call, except it's going to be the max. Right, and we're going to have some values after that, and we'll just print that to make sure it makes sense. Right, and it makes sense. Our largest column is -1. I mean, our smallest column is -1. Our largest column is -2. Right, so now we have no sort. Right, and then we're going to want to return our output, which is going to be an array. So we'll return output here. And like we said, we can generate an array by looping over this range. So we'll say for let I is equal to smallest column. We're going to say, well, I is less than, right, or equal to largest column, I plus plus, and then we can just say output.push map.get smallest call. Not smallest call, it would be I. That makes sense. So this should give us linear time with linear space at worst case in the queue. But let's see. I think this should be the fastest one we've written so far, but the variability. Oh, this must have been part of a daily challenge or something. But yeah, this actually is our best one we've written so far. All of our ones have running 98 milliseconds or 91 or 140. So this is actually the best, right? 96%. So I would say that it's really, really good. And just for the sake of keeping track of this, I'm going to say our time goal is linear time, right? And linear space. And I'd be interested to see how they implemented this on their end, right? If you do the BFS, right, with sorting, you get n log n, right, with O of n space, right? All right, so there's something very similar, min column and max column, right? And I don't think it gets much faster. Oh, wait. Okay, it looks like it goes even further. Oh, maybe not. It's O of n, right, in the space. Be W, right, where what is W? W times H, where is it? So I would say linear time and linear space is good enough. Now I'll just write a note to make sure that we keep that as the goal, time and space complexity, right? And we have number of provinces. It looks like we have trouble counting or we have trouble figuring out the time complexity, right? So let's see if we can make this one make sense. Right, so we have something along the lines of there are n cities. Some of them are connected while some are not. If city A is connected directly with city B and city B is connected directly with city C, then city A is connected indirectly with city C. So A is connected to B, B is connected to C, A is indirectly connected to C by the transitive property, right? The province is a group of directly or indirectly connected cities and no other cities outside of the group. The province is a group of directly or indirectly connected cities and no other cities outside of the group. Okay? You're given an n by n matrix is connected, where is connected I sub j is equal to 1 if the ith city and the jth city are directly connected. And is connected I sub j is equal to 0. Otherwise, return the total number of provinces. This is an interesting problem. We're given an n by n matrix, right? So let's map it to what we see. N by n matrix, right? So this is another way of representing a graph, right, with a matrix, right, with the matrix itself make this bigger so it's easier to read, where the matrix itself represents connections between these values, which makes sense, right? I'm actually not certain what this would be called. So we have this, right? So we always have a connection to ourself, right? And does node 0 have a connection with node 1? Yes, right? Does node 0 have a connection with node 2? No. Right? And we also have to see that we're going to be off by 1 here, right? Node 0 is actually going to be 1, node 1 is going to be 2, and node 2 is going to be 3, right? And we're going to see, does node 2 have a connection with node 1? Yes. Does node 2 have a connection with node 2 itself? Yes, right? Does node 2 have a connection with node 3? No, because there's a 0 here and there's no line here. And 2 has no connections with any node, right? So ultimately, right, we basically want to keep track of the number of provinces, right? And so since a province is a group of directly or indirectly connected cities, right, it basically means, right, that we'd like to be able to model our graph as a relationship of root nodes, right? If 1 is connected to 2, then they're a province, right? That would mean that the total number of potential, basically we're looking for the total number of provinces, but additionally I guess a way to reframe the problem in computer science terms, if we have 3 nodes on a graph, right, we basically want to know how many groups of, how many groups of connections do we have, right? And the groups of connections form a province, right? The number of connections or groups of connections we have is 2, right? If a node is connected to another node, and if this node is connected to another node, they pretty much serve as one province or one group of connected nodes, right? Number of provinces would still be 2 if there was another node for which 2 is connected to, right? And we see here, right, when we have no connection between the nodes, right, then the number of connected groups, right, is actually equal to the number of nodes. So we see, right, is that the number of nodes, right, what we're looking for is the number of connected components, basically, or the number of grouped components, right? And what we can see is that we start with a base number, right, of 3, right? And what we're seeing is, right, the number of nodes equals the number of connected number of nodes starts out as the number of unconnected components, right? And as connections form, what we do is actually decrease number of unconnected components, right? As we decrease the number of unconnected components, we indirectly increase the number of connected components, right? Because connections are forming. So to start, what I'm basically trying to say is that if we have 3 nodes or 3 vertices in this graph, the number of provinces or the number of groups of connected nodes, basically the number of groups of connections are, the number of connected components, right, would be 3, because a node is technically connected to itself, so the number of connected components is 3, right? And so what we're seeing here is that the number of provinces is actually going to be 3 because there's no connection. So when there's no connections, right, what we want to return is simply just the number of vertices, right, because there's no connections. So if that's the case, then I think we can do something which helps with, pretty much always helps with connected components and figuring out what set a group of components might be connected to, right? is union find, which is a data structure that allows us pretty much to test the number of, basically allows us to test, allows us to perform a union when two nodes are indirectly connected or directly connected, which ultimately lets us test whether or not number of connected components, which is what we're interested in terms of the number of provinces. Connected components doesn't really sound right. We're looking for the number of groups of connected, basically the number of groups of components, or the number of the quantity of the sets of the component. It's a hard way to say it actually. Number of groups, how many groups have these components been grouped into basically, or how many sets exist as part of all vertices in the graph, right? And when we start, it's going to be equal to the number of vertices. So basically to start, we're going to have to implement the union find data structure. And so we're going to need two variables to start. We're going to need a root array, which is going to be an empty array to start, and the rank array so we can optimize our union find implementation, right? And so we're going to have a constructor, right? This constructor is going to take the number of vertices, which is going to be a number, and we're going to do some important setting up process here. So we're going to have iteration, right, over the number of vertices, right? And to set up this root array, right, typically, right, this root array, right, each index serves as a mirror to the actual vertice in the graph. So the actual value stored in the array for a particular index goes to serve as the root node for a particular index. So we can say this dot root sub I is going to be equal to, oh no, we're just going to push it on because it's empty to start. Basically, to start, every node's root component or its parent component, where they say its root component is going to be itself. So that's how we're going to start. And then we're going to say, grouped components equals 0 to start, right? And when we get a number of vertices, right, the number of grouped components is going to be equal to the number of vertices, basically, right? Because the number of groups of connected components, right? There's 3 groups of components. Yeah, basically we're looking for the number of grouped components. It's going to be 3 grouped components to start, each in their own group. As connections form, right, the number of grouped components will decrease, right? And for the rank array, right, we can actually just push the value 1 because every node, right, every root node is going to have a rank of 1 to start. Then we're going to need to implement the find function, right? We're going to take a component x, which is going to be a number, and we're actually going to return, right, its root component, right? And to do that, we're going to let temp equal to x, and we're going to basically recursively but iteratively search up through the array to find the highest, or the node that is the root node. The node that is the root node, right, is actually the node's index itself, and the values stored in that index are the same, right? Every node starts out like that, or every vertex starts out like that in union find. So while temp does not equal this dot root sub temp, right, then we're going to say temp is equal to this dot root sub temp, right? Then we're going to return temp. Then we're going to have a union operation, right? Given 2 components x and y, right? We're going to want to be able to create a union between these 2 sets. So we want to fuse this set, this group of connected components y, right, into this group of connected components x. This is going to pretty much overall create a decrease in number of grouped components, right? To start, we're going to need to get the root component of x. We can just do a this.find on x. And we can duplicate root y and do a this.find on y, right? And if root.x does not equal root.y, then we're in business, right? Because we can't perform a union on 2 elements that have the same root, right? It would be a null operation. But if their roots aren't the same, then we know that this operation is ultimately, right, going to decrease the number of grouped components. Right, so we'll say this dot group components minus equal 1. Right, and then additionally, we're going to do some extra work, right? So this is where the union by rank optimization comes in, right? We're going to have to compare the ranks of these roots, right? Because the component with the greater rank, right, is going to have the other component merged into it, right? So if root x's rank is greater than root y, right, then we're actually going to fuse this dot root of root y, right, is now going to be equal to root x, right? So root y is now going to be added into root x's group, right, because its root component is now the same as x, right? Then we're going to keep going. We're going to say else if this dot rank of root y is greater than this dot rank of root x, we're going to say this dot roots of root x, right, is now going to be equal to root y. Otherwise, right, means their rank is the same, and we're just going to default here and say that we're going to fuse we're going to fuse root y into root x, and then we're going to increment root x's rank. And so now what remains is that we just have to load these edges, right, into our union find data structure. So we'll create a new union find, right? Let's say new union find, right? And what's going to be the number of vertices? Well, we know we're given a matrix of connections, so we know that the number of vertices is either equal to the number of rows or the number of columns. To do that, we can just say is connected dot length and just go with the number of rows to start. Then from here, we're just going to iterate over the edges, right? To do that, we're going to have to start row equals 0, row is less than is connected dot length, row plus plus, right? Call is equal to 0, right? And call is going to be less than is connected, so row dot length. But I think we're guaranteed that this matrix is actually uniform, right? Is connected sub I. We guarantee that the column for every row is going to be uniform, right? And we're going to want to change this secondary part right here to call plus plus, and then now we can load in our edges, right? And to do that, we just have to do uf dot union, right, for component. Well, how do we know if there's a component, right? If there's a 1 at this particular index, so we can just say if is connected sub row sub call equals 1, means there's a connection there, right? So we're going to want to do the uf dot union of the first component and the second component, which are actually going to be the row and the column, right? Based on the matrix above, right? Because we have 0, 0 here, right? Then the connection is going to be to itself, but here it's going to be 0, right? Imagine there's a 0 here and a 1 here. The connection is going to be between node 1 and node 2, and that's just because our vertices are going to be 1 index, where our indices in the array are going to be 0 indexed. So the uf.union of row and column, right? And we actually added, right, a variable to keep track of the grouped components, so we can just return uf.grouped components. So this makes sense. Now what's the time complexity, right? We're going to do an n by n iteration over the matrix, right? It's going to be n by n, right? Then we're going to do a operation, right, which is going to be a union operation, which is average to constant time amortized. So I would say that, I mean, not amortized, but I think we would end up with n by n time, right? And our UF data structure right, would definitely be O of V space, because we'd based on number of vertices. But I would say n by n time I want to say n by n time. Or I guess n by n is n squared, so this is an n squared approach. I think union find is n cubed. I think they're not using, are they using the one with union by rank? No, this one doesn't even use union by rank, which would technically would make it n cubed time. Yeah, but I think this comment mentioned, right, with path compression, right, union by rank, I think it'd be O n squared, which would be the same as the previous approaches. So we'll keep that to start. And we know now that the goal time is O of n squared, and the goal space is actually O of n, or O of v. Right, and I'm actually going to double check. What did they say that it was for number of provinces? It said be O of n because the parent array of size n. Yeah, which is technically O of v and O of n would be the same here. So I'll take that. Right, and so we have about 40 minutes left. So I think I'm going to go with our Explorer card to end. So we are back. I think we originally stopped earlier, right, because we were busy, right? I think we wanted to get more DFS work done. We ended up skipping out on evaluate division. I think we lost a chance, right, to get better. So I think we're going to spend even more time on evaluate division, but I honestly think this one seems to be something that this one seems to have more to do with equations, to be honest, than actual disjoint set work, but it remains to be seen, right? We also have optimized water distribution, which I think is likely a hard, right? And it has to do with weighted paths, right? Which we are technically incompatible with, to be honest. But yes, I wonder if there's a way to make this full screen. I don't like this bottom thing. So back, so we had this what we had before, and this one seems relatively impossible. Is there a solution for it? There is. It seems to be asked by quite a few companies, right? Union find, graph, shortest path. So we know this is possible to solve with union find. Can we make it make sense? Can we make this make sense? So we're given an array of variable pairs equations and an array of real numbers values. Right, an array of variable pairs equations and an array of real numbers values, where equation sub I is equal to a sub I, b sub I, and values I represent the equation a sub I divided by b sub I equals value sub I. Each a sub I or b sub I is a string that represents a single variable. We're also given some queries, okay, where query sub j is equal to c sub j, d sub j represents the jth query, where you must find the answer for c sub j divided by d sub j equals question mark. Return the answers to all queries. Single answer cannot be determined. Return -1. Note the input is always valid. You may assume that evaluating the queries will not result in division by 0. That there is no contradiction. So let's map this to our problem statement to start. We're given an array of variable pairs equations and an array of real numbers values. So we have equations and values, which are real numbers, right? And we have equations, where equation sub I is equal to a sub I and b sub I, right? We do have letters a and b, and values sub I represent the equation, Values sub I represent the equation a sub I divided by b sub I equals value sub I. So they're saying that a divided by b, right, gives you 2.0. All right, so we have a divided by b gives us 2.0, right? And then we have b divided by c equals 3.0, right? Interesting. And they want us to return the array of values such that basically we have to figure out a and c, right? Basically what all the values are for a, b, and c. And then we can figure out what a divided by c is, and then we just return those as values. Now they're saying that a divided by b equals 2.0. C equals 3.0. Queries are a divided by c equals question mark. Interesting. Interesting. So we have some equations. How could you get a divided by b to equal 2.0? How could one get a divided by b to equal 2.0? How could one accomplish that? Right, maybe we could do some equation magic just to generate some ideas. Right, I think you could multiply, we have a over b, you can multiply each side by b over it. We had a divided by b and b, and a divided by b multiplied by b over a. Let me reevaluate this, right? Let's say we have 4 divided by 2 equals 2, right? What you would do is you would say this we multiply by 2 over 4. That should actually give you 8 over 8. This does not work well. Let's say we had 4 divided by a equals 2. Right, and to get this answer, you would actually multiply both sides by a over 4. Or maybe you would. I need like a piece of paper. If you had 4 divided by a equals 2, right, then you multiply both sides, something like this, 4 equals 2. You'd multiply by the reciprocal, I think, which would be a. Then we have oh no, I think you actually did the opposite. If you have 4 over a equals 2, I think what you actually do is you multiply it by the reciprocal. You'd multiply it by 1 over 4. Right, equals 2. Then you'd have a equals 2 over 4. Maybe I'm delusional. Oh, no. A equals 2 over 4 would be 0.5. Right, but 4 divided by I think I messed this up bad. If we have 4, yeah, we need like an equation solver or something. Let me see. Okay, maybe I didn't mess up. I think I just had to plug it back in. So I got 0.5, and it's true. 4 divided by 0.5 does equal 2. It says you would transform 4 over a equal 2 so that a only appears in the numerator. A only appears in the numerator. To do that, you have to multiply it by 1 over 4. Right? So what if we took this back to a divided by b? And you guys actually can't see what I'm doing, but yeah, we need to get like an iPad or something so that it'll be easier to show what I'm doing. We have a over b equals 2. Right? Is that what they said in the problem? You evaluate the decision. We have a divided by b equals 2. So if a divided by b equals 2, then we're going to have to multiply a divided by b equals 2. Then multiply, if you want to figure out, let's just say we want to figure out what a is, we could multiply it by the, basically b over 1. Multiply both sides by b over 1. Then we could say a is equal to 2b. That doesn't really help us though. But we know that b divided by c, actually we don't know what that value is. Oh, we know what b divided by c is. B divided by c is equal to 3.0. B divided by c is equal to 3.0. So if we did something similar, right, we could say that b, multiply b over c by c over 1, which would make c equal to 3b. Or we could do something different and multiply b over c by no, yeah, I messed up, right? If you multiply b over c by c over 1, the c's would cancel out and b would equal 3c. Right, but we have no idea what c equals. This one seems a little bit impossible. Yeah, this one seems like a math tick. I don't know if I have the math chops for this one, but it's definitely a space to try and figure it out. Show hint 1. Do you recognize this as a graph problem? Maybe you don't maybe it's impossible to solve for a value here. Maybe it is impossible to solve for a value here. We have AB, right, BC, and to be honest, AB to BC looks like edges to me. So if they look like edges, what would they be sharing? Would their root node be, what would their root node be? Their root node would be what? If AB, BC, yeah, I'm not seeing how this makes sense. Return the answers to all queries. If a single answer cannot be determined, return negative 1.0. Our output is 0.5, negative 1, 1, and negative 1. A, B, B, and C values. Yeah, this is interesting. A over B is equal to 2.0. A over B is equal to right? What if we just assume it's impossible to solve for this equation? We have this values array. Maybe there's something we know that okay, wait, actually, what if we rephrase it, right? We know that we need like something to write on. This is pretty bad. We know that A divided by B equals 2.0, right? And B divided by C equals 3.0. B divided by C equals 3.0, and we know that B equals 3C, so maybe this is actually solvable. If we have B divided by C, right, then we can swap B in for 3C. So we could say 3C divided by C equals 3.0, right? But what if, right, 3C divided by C, wouldn't that just be 2C? 2C equals 3.0, which would mean that 3.0 would be, C would be equal to 1.5. That doesn't make sense though, because the output, well, let's see, right? We said B divided by C equals 3.0. And B is equal to 3C, which would mean B is equal to 4.5. Now, if we do B divided by C, we do get 3.0. What if we do something like, we still don't know what A is. A is equal to 2B. So A would be equal to 9. Is that what they're saying? So if we did A divided by B, we get 2. If we do B divided by C, right, we definitely get 3. Now what if we did A divided by C? A divided by C would be 6. Oh, so we actually maybe we're onto something. It would be 6, right? B divided by C is B divided by C. B divided by, wait, huh? Oh no, I'm getting confused. B divided by A. B divided by A would be 4.5 divided by 9, plus 4.5 divided by 9 equals 0.5. That's kind of strange. A divided by E, we don't actually have E as a variable. A divided by A is 1. X divided by X, that doesn't even exist. So maybe this is solvable. Now, how do you build a method to solve it? You reverse it. I don't have enough space to write on this. How could we reverse engineer the solving and label it as a graph problem? So what did we do? We basically set A divided by B equal to the value at A. Basically said the equation at E sub I is equal to the value at V sub I, which is basically what they said in the beginning, right? And then if you rearrange the equation and you can solve for A, then you can solve for B, and then you can solve for C, maybe. Right? Because that's what we did. What we really did was we swapped in those values, right? We said that if A divided by B equals 2.0 and B equals No, I think we had A divided by B equals 2.0, right? And then B divided by C equals 3.0. Right? Then we can say that B swapped into, if we swap B in for C, what we solved B for B was 3C. And I guess since it's division and the variables are simple, we can always just make it equal to the values. We'd say B is equal to 3, basically. 3C so yeah, I think we have a way to figure out this thing. We go from A to B, B to C, right? It's kind of like a transitive thing. Or we get to C, which makes sense. When we get to C, we want to solve for B. To solve for B, I guess we have to go to Interesting. So it looks like we can get a value out of this, but I think building something that can parse strings and make calculations doesn't really make much sense. So how can we keep how can we make this make sense? We model this as a graph of some sort. Right, we have A, B, and C. Draw a line between them, A to B, B to C, and you can only get the value for A. In terms of the equation, you can only get the, basically you have to traverse the graph until the end, right? You have to get, I guess, maybe not in the end, there's no real end. But I guess this could be, if we viewed it as a directed graph, but it's not directed since you want to be able to go from B up to C, so it's undirected. So union find lets us view graph in the sense of its connected components, right? And if we have two competing sets of equations, right, maybe we could only solve graphs, right, in groups, in these connected groups, right? And we can only solve them in these connected groups. We can only solve them in these connected groups, and union find or something where we can visit edges of a graph that is, we only visit a subsection of graph that is connected. Maybe that's valuable. If that's the case, how does A, B, and C allow us? Right, so we can view this as as one connected component, right? So we can solve for it. So our queries can actually be, multifaceted. query length can be up to 20. Does that mean we automatically assume multiplication for BC and CD? B times C divided by CD. Query sub j is equal to C sub j comma D sub j. Now, if we were to model this, maybe we can make more sense if we model it from the sense that the queries we'd like to process, right? Presumably the query processing part would be kind of irrelevant from the first part. Once we figure out what A, B, and C are, right, it doesn't quite matter. But actually what we did earlier, how we did that, right, to figure out what the value of it was, right, we need to use the query where A divided by C equals 2.0. I think maybe what we're seeing here is that you can use A or C to solve for it. Right, A or C. No, this doesn't make sense. A or wait, huh? A divided by B, right, gives you 2.0. So you actually don't need the queries. The queries is what we're outputting after we figure out the values. So we have A divided by B equals 2.0. Values equals 0.5, queries equals A, B, BA, AC, X, Y. We reverse engineered it one time. Maybe looking at it, I'm trying to see how maybe looking at it from a group of connected components could be useful. For example, in example 2, we have equations A, B, right, and then we have C, right? But then oh no, yeah, we have B, C, right? So you have an edge between A and D, A and B, B and C, right? And then there's actually another C and D. All these are technically strung together. And so what is that saying? It means we can only calculate this starting from the top node. We can only calculate this starting from the root node, right? I guess which would be A, right? The connection between A and B. I guess if they gave us this equation in any order, right, we would also still have a similar problem. And I guess they could change the letters too so you couldn't sort it, since what really matters is that you can't process CD without going to the top, or they're starting from the root node. The root node is A, and I guess that's why this is a union find problem, because you want to know what the root node is, right? I guess presumably if all these queries can be solved, then if all these queries can be solved, well, they can't all be solved, right? But it seems like the method by which they can't be solved is by using a vertex which does not exist, right? Even here they use A and C, only A and B exist. So anything that doesn't include those has to be -1, right? So if presumably all the queries use vertices that only exist, then this equation must be solvable. If that's the case, it's only solvable top down, because you can't start from D, you can't start from C, and you can't start from B. You have to start from A, which is the root node. So maybe in the end, the whole part of union find in this sense is just to know what the root node is. If we know what the root node is, maybe we can calculate them going forward. I just don't understand how you would write the code to automatically solve the function. For example, you have A, B, B, C, right, which is our graph here. The values 2.0 and 3.0. We know that A divided by B equals 2.0. A divided by B equals 2.0. Maybe another way is if we say A divided by A over B equals 2, right? What if we have another A over B equals 2, and then we multiply it by 1 over A? All right, this would cancel out the A and say B is equal to 2A. Right, if B is equal to 2A, then we can push this back into our original equation, which would be A over 2A equals 2. You could divide both sides. Now you could multiply both sides by 2 over 1. You get A over A equals 4. Which doesn't make sense actually, because A is supposed to equal 9. A over A equals 4. So that doesn't quite make sense. I think you have to use another equation like we did before. We had A over B equals 2.0, and then we had B over C equals 3.0. So maybe it's only solvable in the sense that you need to have your root node, right, and then your next node after it. But I can't see how you automate. The calculation, unless maybe there's a repetitive operation we can apply without implementing an entire equation solver. I think we're onto something with the root component. It's not the way we solved it originally, so let's try another approach. Yeah, you guys can't really see me writing, but I have to get an iPad or something so it can actually do something with this. So we have input, we have equations, right? And like we mentioned, we have A over B, right, equals 2. A over B equals 2. Additionally, that B over C equals 3. Since it's always division, maybe what we can do is just say that B is equal to 3C. B is equal to once B is equal to 3C, no, that doesn't make sense. 1 over B, we have C is equal to 3B, or we could multiply it. How did we even solve this the first time? This makes no sense. A over B equals 2. 4 over A equals 2. Where did we get 4 from? Oh, that was just something we were testing. A over B equals 2. B over C equals 3. What is going on? A over B equals 2. B over C equals 3. 2C equals 3. 3. C over C. 2C equals 3. Yeah, we just need a better method of figuring out. Yeah, we need to do some basic. We need to go back. We need to do some algebra. But I'm going to stop it there. Day 56.